Okay, so our next speaker is Alfonso Tortorella from Leuven, and he will speak on contact dual pairs.
Okay. First of all, many thanks to the organizers and so to Daniele, Henrique, and Amelia for the opportunity to be here in Rio and meet a lot of people working in Poisson geometry. As just said, my talk is about contact dual pairs, and is based on joint work with Adara Blaga and Cornelia Wiesmann from Timișoara, and with Maria Amelia. In order to motivate the introduction of this notion of contact dual pair, I will start with a brief review of dual pairs in Poisson geometry. As you may know, a symplectic dual pair consists of a pair of Poisson maps defined on the same symplectic manifold, such that the fibers of these two legs are the orthogonal complement of each other with respect to the symplectic form. And additionally, you say that this dual pair is full when these two maps, these two Poisson maps, are surjective submersions. Tracing back to Sophus-Lee, dual pairs have their modern origin in the study of the local structure of Poisson manifolds by Alan Weinstein. Indeed, if two Poisson manifolds fit into a symplectic dual pair, then their local structure is very closely related. More precisely, if this dual pair is full and the two legs have connected fibers, then this relation here establishes a one-to-one correspondence between the symplectic leaves S1 of the Poisson manifold M1 and the symplectic leaves S2 of the Poisson manifold M2. And additionally, it induces an anti-isomorphism between the transverse Poisson structures to the corresponding symplectic leaves. These actually led to the introduction and investigation of Morita equivalence for Poisson manifolds. As one main source of examples of dual pairs in Poisson geometry, we have symplectic groupoids. Indeed, if G is a symplectic groupoid over the manifold M with induced Poisson structure pi on M, then this diagram formed by the source and target map of the groupoid form a full symplectic dual pair. Moreover, if symplectic dual pairs also pop up naturally in connection with the symplectic reduction, indeed, if we have a Lie group G, a free, proper, and Hamiltonian action of a Lie group G on a symplectic manifold M with equivariant moment map, then the moment map together with the quotient map form a symplectic dual pair. Moreover, recently, the notion of dual pair has been generalized from the setting of Poisson manifolds and Poisson maps to the setting of Dirac manifolds and forward Dirac maps by Ionuz and Pedro. And they have applied this generalized notion of dual pair in order to obtain alternative, more conceptual proofs for the existence of presymplectic realization of Dirac manifolds and for the normal form theorem around Dirac transversals. I tried with this to highlight the central role played by dual pairs in Poisson geometry. And now, because of the close relation existing between, on the one hand, symplectic and Poisson geometry, and on the other hand, contact and Jacobi geometry, this makes pretty natural to wonder what, if any, is the contact analog of simplectic dual pairs. And essentially, my talk aims at proposing an answer to this question. And it has the following structure. First, in order to set up what will be the general framework of the talk, I will give a brief review of contact and Jacobi geometry, making use of both the line bundle approach to these geometries and the alternative but equivalent approach via symplectization and Poissonization. Then I will introduce our proposal for the notion of contact dual pair with the motivating example coming from contact groupoids. And I will mention one of our main results about contact dual pairs in connection with the local structure of Jacobi manifolds. And moreover, I will show how contact dual pairs naturally pop up in connection with the contact reduction now. In the very last part of the talk, if time permits, I will also mention an extension of this notion of dual pair from the setting of Jacobi manifolds to the setting of Dirac-Jacobi manifolds, in analogy with what Pedro and Yunus did in Dirac geometry. And this part is based on joint work with Jonas Schnitzer. Okay, so I will start with this brief review of Jacobi and contact geometry. There will be a lot of overlapping with the talk by Luca. I didn't know that he was going to talk about Jacobi geometry until recently. Okay? And so I apologize for that. Maybe we are just helping you to better understand the talk of Camillo for tomorrow. Okay, so let's start with what will be the conceptual background for these two approaches to Jacobian contact geometry, the line bundle approach and the approach by symplectization and Poissonization trick. Okay, so as also Luca said, and you already know, a derivation of a line bundle is an R-linear map delta from the module of line bundle section to itself, such that for some unique vector field on M, called the symbol of the derivation, this Leibniz-like identity is satisfied. So derivations of a line bundle are L, are sections of this vector bundle here, dl over M, and so they are vector bundle morphisms over the identity map of M from the first jet bundle of L to the line bundle itself. This vector bundle dl has a natural structure of the algebroid, and it's called the gauge algebroid or Ratti algebroid. And moreover, it has a representation on L, where the Lib bracket is just the commutator of derivations. The anchor map is given by the symbol map, which sends each derivation to its symbol. And the representation is of dl on L is the tautological one. You just act with the derivation on the section of the line bundle. The construction of the gauge algebroid is functorial, meaning that for any regular line bundle morphism, there is an induced gauge algebroid morphism. Here and in the following, by regular line bundle morphism, I mean that the line bundle on each fiber separately is a linear isomorphism. And so this, as we will see later, will allow me to pull back sections from sections of L2 to sections of L1. Okay? Out of the data encoded into the gauge algebroid and its tautological representation, I can construct two additional tools. One is the Schouten-Jacobi bracket. I mean, a graded Lie bracket on the shifted graded space of skew-symmetric multiderivations of the line bundle. Roughly speaking, this Schouten-Jacobi bracket is to multiderivation exactly like the ordinary Schouten-Noisy bracket is to multivector fields on a manifold. Additionally, I can also construct the Der complex, which consists of the graded space of Atiyah forms, L-valued Atiyah forms, already mentioned in, and the Der differential, already mentioned in the talk by Luca. And this Der complex which is acyclic, is nothing but then the algebroid theorem complex of the gauge algebroid with coefficients in its tautological line bundle, on its tautological representation. Okay? This is essentially all what you need to know in order to understand the line bundle approach to Jacobi and contact geometry. In order to illustrate the alternative and the equivalent approach via symplectization and Poissonization, let's consider a principal bundle P over M with the structure group Rx, the multiplicative group of non-zero real numbers. And now we can single out the C infinity of M module of degree 1 homogeneous functions, which are those functions on P which satisfy this homogeneity condition written down here. Further, we can single out the C infinity of M submodule and Lie subalgebra of homogeneous multivector fields on P, which are those multivector fields on P which satisfy this homogeneity condition written down here. And so this homogeneity condition, the degree of homogeneity of these multivector fields depend on their tensorial degree. Finally, we can single out this C infinity of M submodule and subcomplex formed by the degree 1 homogeneous differential forms on P, which are those differential forms on P which satisfy this homogeneity condition here. Okay, and now we can see that for any given line bundle L over a manifold M, we can construct its slit dual, which is just the dual of the line bundle with the zero section removed. This one is clearly a principal R-cross bundle. And in the opposite direction, given a principal R-cross bundle P over M, since Rx is a GLA, the general linear group of R, we can construct the associated bundle, which is a line bundle, and it's actually the dual of the tautological bundle over M associated with P. These two constructions are called the homogenization of the line bundle and the projectivization of the principal R-cross bundle, and they are actually functors, not just functors. They establish an equivalence of a category between the category of line bundles with regular line bundle morphism that we introduced before and the category of principal R-cross bundles with R-cross equivariant maps. In addition to that, we can also there exists also a C infinity of M module isomorphism, identifying sections of the line bundle with homogeneous functions on its homogenization, L tilde. Second, there exists a C infinity of M module Lie algebra isomorphism, which now identifies the multi-derivations of the line bundle L with the homogeneous multivector fields on its homogenization, L tilde. And finally, there is a C infinity of M module and cochain isomorphism, which identify their complex of Atiyah forms, L-valued Atiyah forms, with the RAM complex of homogeneous differential forms on L tilde. And this is essentially what one needs to recall in order to present later the approach to contact and Jacobi geometry via homogenization and Poissonization trick. Okay, and so let's move on to this brief summary of contact and Jacobi geometry. Following Marle, a Jacobi bundle is a real line bundle L over a manifold M, additionally equipped with a Jacobi or Jacobi bracket, a Jacobi structure or a Jacobi bracket, which is nothing but then a Lie bracket on the modulo of line bundle sections, which additionally is a B derivation. And then clearly a Jacobi manifold is a manifold equipped with a Jacobi bundle over it. For our aims, it will be also convenient to point out that a Jacobi structure on a given line bundle L is nothing but then a Moret-Cartan element in this grade Lie algebra. And so they are just degree 1 elements in this grade space, and so they are B derivations because of the shift, which additionally satisfy the Moret-Cartan equation. Now we have introduced the object in our category. We can go on introducing the morphisms of our category. a Jacobi morphism is a regular line bundle morphism, phi from L1 to L2, such that the now well-defined pullback of sections, which sends sections of the line bundle L2 to sections of the line bundle L1, these pullback of sections has to preserve the Jacobi brackets. In the special case, in the special corientable case, I mean when this line bundle L over M is the trivial line bundle, then a Jacobi structure over it reduces to a Jacobi pair, following the terminology introduced by Lichner-Horowitz. This Jacobi pair consists of a bivector field pi and a vector field E, which satisfy a compatibility condition, written down here in terms of the ordinary Scout and Danois bracket of multivector fields. So that in particular, when the vector field E is 0, one recovers Poisson manifolds as instances of Jacobi manifolds. And so Poisson manifolds are a special case of Jacobi manifolds, but also on the other way around, one can see Jacobi manifolds as a specialization of Poisson manifolds, because the C infinity of M modulo isomorphism and the algebra isomorphism that we introduced before, from multi-derivations of a line bundle to homogeneous multivector fields on its homogenization, L tilde, sends Moret-Cartan elements of one Lie algebra to Moret-Cartan elements of the other Lie algebra. And so, in view of this, the homogenization and dehomogenization functor establish an equivalence of category between the category of Jacobi manifolds with Jacobi morphism that we have just introduced on the previous slide, and the category of homogeneous Poisson manifolds, by which I mean an R-cross principal bundle equipped with a Poisson structure, which at the same time is homogeneous according to the definition we saw before. And here the morphisms are the R-cross equivariant Poisson maps. As a consequence of this equivalence of category, since for any Lie algebra G, it's the linear Poisson structure on G star is homogeneous, once we remove the 0 from G star, then we obtain that on the tautological bundle over the projectivization of G star, there exists a canonical Jacobi structure. Okay. As one large class of examples of Jacobi manifolds, we have the locally conform asymplectic or LCS manifolds. Here, slightly generalizing the original definition due to Isu-Weismann, we say that an LCS structure on a manifold M consists of a line bundle L over M with a representation of the tangent algebroid Tm plus a non-degenerate true cocycle in the de Rham complex of Tm with the values in the representation L. In the special case, when the line bundle is the trivial line bundle over M, then an LCS structure, given by this definition, reduces to a pair formed by a closed real-valued one-form eta on M and a non-degenerate two-form omega on M, which satisfy this condition here. This condition here encodes the closeness condition encodes the flatness of the connection, and the closeness condition here is translated in this condition here, which gives back us the original definition by Isu-Weismann. Given now an arbitrary LCS manifold, for any section of the line bundle L, there exists, we have the associated Hamiltonian vector field, which is defined this way. So the map from line bundle sections to their associated Hamiltonian vector field is a first-order differential operator from L to Tm. Consequently, this bracket written down here is a B derivation, and moreover, it satisfies the Jacobi identity because omega, the true form, is closed. this Jacobi structure fully encodes the LCS structure we started with. As another large class of examples of Jacobi structures, we have the contact structures. And here again, I'm repeating many of what already Luca said. As you know, a contact structure on a manifold M is equivalently described by either a contact distribution H on M, I mean an hyperplane distribution which is maximally non-integrable, or by a contact form theta on M with values in some line bundle which is unique only up to line bundle isomorphisms. And here, let me recall that here, the maximally non-integrability condition on the hyperplane distribution H means that the associated curvature true form defined in this way is non-degenerate, fiber-wise non-degenerate. In the orientable case, when this line bundle L over M is the trivial line bundle, then we get that this contact form is an ordinary real-valued one form on M, and the maximally non-integrability condition on H, the kernel of theta, translates in this condition, which is the usual defining condition for global real-valued contact forms on a manifold M. And again, for any contact structure, we have an associated Jacobi structure, which fully encodes the initially given contact structure. It's defined in this way, where we have this x lambda denotes the associated vector, Hamiltonian vector field, or Reb vector field associated with the line bundle section lambda, and which is uniquely determined by these two conditions. First, x lambda has to be an infinitesimal automorphism of the contact distribution. It generates a one parameter subgroup of contactomorphisms. And moreover, once we plug in x lambda into the contact form, the line bundle section that we get is exactly lambda. Before moving forward, it may be convenient for our aims to point out the existence of alternative equivalent descriptions of contact structures on a manifold M. First, we have that this map here from L-valued one form on M to L-valued at tier 2 forms establish a one-to-one correspondence between the contact forms on M with values in L and the symplectic Katia forms, the L-valued symplectic Katia forms, which, as Luca said, are non-degenerate two cocycles in the Dirac complex. Moreover, these two identities here, these two relations here, establish a one-to-one correspondence between now non-degenerate Jacobi structures, which are those Jacobi structures J, such that the associated vector bundle morphism, which goes from the first jet bundle to the gauge algebroid, is a vector bundle isomorphism. The other term of the correspondence are symplectic Katia forms, which we just have introduced, and the other term are the homogeneous symplectic form on the homogenization of L, which are just closed, non-degenerate, degree 1 homogeneous forms on L tilde. Combining these two partial results, we obtain that homogenization and dehomogenization establish an equivalence of category between contact manifold and contactomorphisms, where contactomorphisms are diffeomorphisms preserving the contact distributions, and the category of homogeneous symplectic manifolds with R-cross equivariant symplectomorphisms. Again, here, by homogeneous symplectic, yeah, I should have said that. What I mean by homogeneous symplectic, here, by homogeneous symplectic manifold, I mean an R-cross principal bundle equipped with an homogeneous symplectic form. And this is what Luca was calling homogeneous, finite homogeneous Poisson, or finite homogeneous symplectic. Okay, and this is essentially, this equivalence of category is encodes essentially the symplectization trick for the description of contact structures. As a consequence of this equivalence of category, since for any manifold on the cotangent bundle of M, the canonical symplectic form is homogeneous once we remove the zero section from T star M. We obtain that on the projectivization of T star M, there exists a canonical contact structure. Okay, now here we come to what was supposed to be the core of the talk, contact dual pairs. In order to motivate our definition, I will try to show you how our definition naturally emerges from the theory of contact groupoids. And so let's recall that given a Lie groupoid G over G naught, a multiplicative contact structure on G can be equivalently described by a contact distribution H on G, which additionally is multiplicative, meaning that H is a widely subgroupoid in the tangent groupoid of G. Or by a contact form theta on G with values in T star L naught, where L naught is a line bundle over the space of objects G naught, which brings a representation of the Lie groupoid G, and such that this contact form is now multiplicative, meaning that this identity written down here is satisfied. Then clearly a contact groupoid is a Lie groupoid equipped with a multiplicative contact structure. Again, the symplectization trick allows us to get an alternative description of contact groupoids. First, we say that a symplectic groupoid G over G naught is homogeneous when G has an additional structure of R cross principal bundle, such that first, all the groupoid structure maps are R cross equivariant, and second, the multiplicative symplectic form on G is homogeneous of degree 1 with respect to the R cross section on G. Then the homogenization and dehomogenization induce a one-to-one correspondence between, on the one hand, homogeneous symplectic groupoids we have just introduced, and contact groupoids. As a consequence of this, since for any Lie group G, the cotangent groupoid is a symplectic groupoid over G over the dual of its Lie algebra once we equip it with the canonical symplectic form, and it becomes homogeneous once we remove the zero section from the cotangent bundle. We obtain that on the projectivization of T star G is a contact groupoid over the projectivization of the dual of the Lie algebra. And this structure is canonical, doesn't depend, just depends only on the Lie group. Okay, let's see now how precisely how contact dual pairs emerge from contact groupoids. Let's take a contact groupoid G over G naught, where this multiplicative contact structure is described by a contact form or equivalently by the multiplicative contact distribution. And let's set L equal to the quotient line bundle of TG mod the contact distribution. Then left and right translation induce regular line bundle morphisms from this line bundle, quotient line bundle L to the line bundle L naught, bringing the representation. And these two regular line bundle morphisms cover respectively source and target map of the groupoid. Furthermore, there exists a unique Jacobi structure on the line bundle with the representation, such that the true maps in this diagram, notice the minus sign here, are Jacobi morphisms. In any contact groupoid, one can see that the following three conditions are satisfied. First, the contact distribution is transverse to both the S fibers and the T fibers of the groupoid. Second, each section of the quotient line bundle L, which is constant along the S fibers, Jacobi commute with any section of the line bundle L, which is now constant along the T fibers. Third, the S vertical part of the contact distribution defined here is, and the T vertical part of H are the orthogonal complement of each other with respect to the curvature 2 form associated with the contact structure. So what we do is to take these three properties satisfied by an arbitrary contact groupoid as our axioms for dual pairs in Jacobi geometry. So we can state our definition as follows. Let's consider a contact manifold and a pair of Jacobi morphisms defined over it. Then we say that this diagram is a contact dual pair if this list of three conditions is satisfied. Again, the contact distribution has to be transverse to the fibers of the two maps underlying the line bundle morphisms. The map small phi 1 going from M to M1 and the small phi 2 going from M to M2. Second, any section of this line bundle constant along the phi 1 fibers and Jacobi commute with any section of this line bundle constant along the phi 2 fibers. And third, the phi 1 vertical part of H and the phi 2 vertical part of H are the orthogonal complement of each other with respect to the curvature 2 form. Okay, this definition was designed exactly in order to recover contact groupoids as an instance of a contact dual pair. But now you can wonder what exactly is the geometrical meaning of this list of apparently weird conditions. And what we prove is that this diagram here is a, then I say that this contact dual pair is full when the underlying two maps are surjective submersions, exactly like we do in Poisson geometry. Okay, I was saying that this pair of Jacobi morphisms defined on the same contact manifold is a contact dual pair, meaning that it satisfies this list of three conditions if and only if the kernels of the induced gauge algebroid morphisms are the orthogonal complement of each other with respect to what? With respect to the L-valued symplectic Atia2 form corresponding to the given contact structure on M, which is an L-value. Okay. Yeah, if you remind the definition of what is a L-value symplectic Atia2 form, you can see that this is a meaningful condition. Okay? These are sub-bundle inside of DL, and omega is an L-value non-degenerate true form on DL. Okay? And so this is the more geometric description, more compact and more geometric description of the definition that we were searching for. And so let's move on to what can be seen as the main property of contact dual pairs in connection with the local structure of Jacobi manifolds. And so for that, I need to recall, again, with some overlap with the talk of Luca, some classical result about the local structure of Jacobi manifolds. First of all, any Jacobi manifold comes equipped with a characteristic foliation. Characteristic foliation, which is the integral singular, the singular foliation integrating the singular tangent distribution that we obtain as the image of the vector bundle morphism from the first jet bundle to the tangent bundle given by the composition of the sharp map of the Jacobi structure, which goes from J1L to DL, and the anchor map, or the symbol map, which goes from DL to TM. In the special case when this characteristic distribution is the whole tangent space, then we say that the Jacobi structure, the Jacobi manifold, is transitive. Now there is a classical result by Kirillov, which consists of two parts, according to which first in a Jacobi manifold, each characteristic leaf, each leaf of this characteristic foliation inherits from the ambient Jacobi structure a structure of transitive Jacobi manifold. The second part is a complete characterization of the transitive Jacobi manifolds, according to which a odd-dimensional transitive Jacobi manifold is nothing but then a contact manifold, and an even-dimensional transitive Jacobi manifold is nothing but then an LCS manifold. So not just contact LCS manifolds are not just examples of Jacobi manifolds, but they are actually the building blocks of any other Jacobi manifold. The second theorem that I need to recall is due to Dasor, Lichtenowitz, and Marle. And according to the result, in a Jacobi manifold, each characteristic leaf inherits a transverse structure. More precisely, each even-dimensional leaf, each LCS leaf inherits a transverse structure which is a Jacobi structure. On the other hand, each odd-dimensional leaf, each contact leaf in a Jacobi manifold inherits a transverse structure which is now a Poisson structure of homogeneous type, which is what Luca was calling infinitesimal homogeneous Poisson. Okay, these are the two results that all what you need to recall about the local structure of Jacobi manifolds. And so we are now in condition to state our main result about full contact dual pair. So we consider a full contact dual pair, where full means that the underlying maps are surjective submersions. And we additionally require that the fibers of these underlying maps are connected. Then we prove that this relation establishes a one-to-one correspondence between the characteristic leaves of one Jacobi manifold and the characteristic leaves of the other Jacobi manifold. Moreover, if S1 and S2 are two corresponding characteristic leaf, then they are both even-dimensional, and so LCS, or they are both odd-dimensional, and so contact leaves. Additionally, there exists a close relation between the inherited transverse Jacobi structure of the corresponding leaves, so that if we know one structure, we can reconstruct the other one. And third, there exists a canonical anti-isomorphism between the transverse structure to the transverse structures of the two corresponding characteristic leaves. And this is the complete analog in the Jacobi setting of the result obtained by Weinstein for dual pairs in Poisson geometry. In the next to the last part of the talk, I would like to mention how contact dual pairs emerge from contact reduction. So I may need to recall what is a contact action of a contact groupoid G on a contact manifold M. And that's just a map, capital Phi, from the fiber product of G and M over G naught to M, satisfying the usual groupoid action axioms, such that now the groupoid action and the contact structures on G and on M are related by a certain compatibility condition. This compatibility condition can be equivalently phrased in two ways. First, it can be phrased in terms of the contact distributions, as written down here. Second, it can be phrased in terms of the contact distributions on G and on M. And this phrasing of the compatibility condition requires that the moment map of the action can be lifted to a regular line bundle morphism from the line bundle over M to the line bundle over G naught, so that now this condition written down here is satisfied. So as a first example of a contact groupoid action, we obtain that for any contact groupoid G, the multiplication is a left contact action of the groupoid on itself with the moment map now given by the target map. Okay, as a second example of a contact action, contact groupoid action, we can consider an action of a Lie group G on a manifold M with the induced action zeta of the Lie algebra on the manifold. And we can equip the manifold M with a contact structure. Then we further assume that the Lie group act on the contact manifold by contactomorphisms, so the action preserves the contact distribution. And we also require that the G orbits are transverse to the contact distribution on M. Under this assumption, this assumption gives rise to a contact action of the contact groupoid that we saw before, the one obtained by projectivization of the cotangent groupoid of G over G star, on the contact manifold M, where the moment map and the action are defined by these two formulas written down here. After having recalled the definition of contact groupoid action and having introduced two examples of contact groupoid action, we can see how we get contact dual pairs from contact reduction. So let's consider a free and proper contact action of a source-connected contact groupoid G on a manifold M with the moment map mu. And let's assume additionally that this moment map is surjective and it has connected fibers. Then under this hypothesis, we can prove that the moment map is also a submersion, and it can be lifted to a regular line bundle morphism from the line bundle over the contact manifold M to the line bundle L0 over the space of objects. And this just because of the definition of contact groupoid action, but this lifting turns out to be a Jacobi morphism. Second, one can prove that there exists on the quotient line bundle a unique Jacobi structure such that the quotient map is a Jacobi morphism. Here we are using the fact that since the Lie groupoid, the action is contact, the action of G on M can be lifted to an action of G on the line bundle over M. Okay, this is the setup that we have. And what we prove is that in this situation, this diagram here, formed by the quotient line bundle morphism and the lifted moment map, is a contact dual pair with additionally connected fibers. Having realized that under these assumptions there exists this contact dual pair, allow us to get a new insight on the contact groupoid action, contact groupoid reduction by Marco and Chen Chang. Precisely, we can reprove that for any G orbit, these reduced orbit spaces inherits transitive Jacobi structures, and these reduced orbit spaces give exactly the characteristic foliation of the quotient Jacobi manifold. Okay, and this is what we proved about contact dual pairs and contact reduction. Since I still have time, I can try to tell you something about dual pairs in this generalization that we get together with Jonas. And so again, here I'm going to review some background material which was already mentioned by Luca. As Luca said, in the role played by the generalized tangent bundle in Dirac geometry is now in Dirac-Jacobi geometry played by the omni-Lie algebroid of the line bundle. for any line bundle L, the omni-linear algebroid consists of this vector bundle, which is just the direct sum of the gauge algebroid and the first jet bundle. We additionally keep this vector bundle with the L-valued non-degenerate product given here, and the Dorfman-like bracket defined by this formula, where we are using the Cartan calculus on the Lie complex, which makes sense since the Lie complex is just the Lie algebroid complex of the gauge algebroid with values in its tautological representation. And now what is a Dirac-Jacobi structure on a certain line bundle? It's a vector subbundle, Carly L, in the omni-linear algebroid, which satisfies two conditions. First, it's Lagrangian with respect to the non-degenerate L-valued product, and it's involutive with respect to the Dorfman bracket. Then, a Dirac-Jacobi manifold is a manifold equipped with a line bundle over it and a Dirac-Jacobi structure on the line bundle. Again, as Luca said, for any Jacobi structure on a line bundle L, the graph of the sharp map is a Dirac-Jacobi structure, and similarly, for any precontact structure encoded by a L-valued presymplectic form, its graph is a Dirac-Jacobi structure. As in Dirac geometry, you have forward Dirac map. In Dirac-Jacobi geometry, you have forward Dirac maps, and they are defined in complete analogy with what you do in Dirac geometry. And now we can state our definition of dual pairs in Dirac-Jacobi geometry that one may also call precontact dual pairs. Then we have a pair of forward Dirac morphisms defined on the same precontact manifold. We assume also that the underlying maps phi1 from M to M1 and phi2 from M to M2 are surjective maps. Then this diagram is a dual pair if these three conditions are satisfied. First, the kernels of the two gauge algebroid morphisms induced by these two regular line bundle morphisms are orthogonal. Second, the intersection of the kernels of these gauge algebroid morphisms and the kernel of the precontact structure is 0. And third, the underlying manifolds M, M1, and M2 satisfy these dimensional relation written down here. Then, once we take this as definition of dual pair, we get that each precontact groupoid naturally gives rise to a precontact dual pair, exactly like contact groupoids give rise to contact dual pairs. And each contact dual pair is already a precontact dual pair. This is what we proved with Jonas about the existence of self-dual pairs in analogy with what, in exact analogy with what Jonuts and Pedro did in the Dirac setting. So what we prove is that for any Dirac-Jacobi manifold, any Dirac-Jacobi manifold fit in a self-dual pair. I mean, a precontact dual pair like this one. And the proof is moves along the same line of the proof given by Pedro and Jonut. And so what we do is to single out a non-empty class of spray derivations. They are not spray vector field, they are spray derivations of this pull-back line bundle. We take the line bundle over M, and we pull it back to the sub-bundle which encodes the Dirac-Jacobi structure. For any choice of a, we fix an arbitrary spray derivation, then we can fix an arbitrary spray derivation V, and using its flow, which consists of a one-parameter group of line bundle automorphisms, we construct these L-valued presymplectic form on these pullback line bundle, where omega can, currently omega can is the symplectic Atiyah form on now this pullback line bundle, the pullback to the first jet bundle, which corresponds exactly to the canonical Cartan contact structure existing on the first jet bundle of an arbitrary line bundle, and then up to restrict to a suitable neighborhood of M in curly L. And this definition, and we obtain in this way a self-dual pair for the given Dirac-Jacobi manifold. And as a consequence of this, the existence of this self-dual pair, one can reprove the existence of pre-contact realizations of Dirac-Jacobi manifold, and one can reprove the normal form theorem around Dirac-Jacobi transversals. I think that I can stop here. Many thanks for your attention. In these 2 slides, I collected some helpful references. And again, many thanks for your attention.